Hello, I'm Seunghun from the MF Lab at Korea University. This presentation is about our paper titled Advancing Bayesian Optimization by Learning Correlated Latent Space. If we have a black box function, which means we can evaluate the function, but we cannot get the gradients and derivatives of this function, and we want to optimize that function, then Bayesian optimization is used in such scenarios. This method is widely applied in areas such as automated design or drug discovery. However, the feasible set is often complex. This means high-dimensional, structured, or discrete. Latent space-based optimization can be the solution. It maps the input into a latent space using a pre-trained autoencoder and then performs Bayesian optimization in this latent space. Latent space-based optimization follows this process. At first, there is a dataset in the input space. This dataset is then mapped into the latent space through this encoder. In the latent space, a surrogate function, that is a probabilistic model, is trained to approximate the function of these latent vectors and its corresponding objective value. And new candidates are selected based on the surrogate function and then mapped into the input space through the encoder. However, this optimization is not directly conducted in the input space. Two main problems, that is the gap in here. The first gap is the misalignment between the latent space and the black box objective function. And the second gap is the imperfect matching between the input space and the latent space. Our method CoBO aims to mitigate these gaps. We propose two regularizations to align the latent space with the objective function. The one is the Lipschitz regularization, which increasing Lipschitz continuity. This regularization improved the correlation between distances of the latent space z and differences of the objective function values y. We proved theorem 1, that means minimizing L maximizes the lower bound of the correlation between the latent space O and the objective function values. And the second is latent space regularization. That prevents a trivial solution where the scale of the latent space merely grows by Lipschitz regularization. It is the align loss for alleviate gap 1. And we suggest the loss weighting to align promising areas of the latent space with the input space. Our weighting function is lambda, and this function focuses on minimizing gaps in areas with high objective function values y. We weight the Lipschitz regularization and reconstruction loss as follows. It is our experiments for molecule design task and arithmetic expression fitting task. It is our analysis for correlation improvement. The plot shows the Pearson correlation values between the latent space distances and objective value differences. The orange one is the model with our align loss, and the blue one is the model without it. That means our align loss enhances the correlation values. This is our analysis to visualize the impact of our align loss. The plot shows the objective function values within the latent space. The model without align loss on the left side and the model with align loss on the right side. As you can see, our align loss makes smoother landscapes in the latent space, which encourages more efficient optimization. This is our pseudocode. And as the conclusion, we propose correlated latent space Bayesian optimization to bridge the inherent gap in latent space Bayesian optimization. Then we introduce two regularizations to align the latent space with the black box objective function. Then we present a loss weighting scheme based on the objective values. Lastly, we demonstrate extensive experimental results and analysis on 9 tasks using 3 benchmark datasets. Thank you for listening.